button to say that Hong has been our adjunct faculty at GIFR.
Right, yeah.
Yes.
Yeah, so I have intended to come back much more often, but yeah, so it's still great to be back, at least virtually. So yeah, so today I'm going to talk about some work which I'm trying to finish soon with my student Shreya Vardhan, and this, yeah, hopefully appear in a week or so. So so let's us just consider, say, some quantum many-body system in the far from equilibrium pure state. Say, you imagine a gas or particle in the box, and then of course eventually the particle will spread out, and for all purpose, if you only can make, say, local measurements or some kind of microscopic measurement, and then you find that this is behave like a thermal equilibrium, okay? And so the system will eventually approach some kind of equilibrium, but still remains a pure state. And it's very hard in general to tell whether this is actually a pure state or a mixed state, just from some kind of local measurement, without knowing fine detail, say, of microscopic quantum mechanical information. And actually, this is precisely the situation we face, yeah, the kind of difficulty we face in the evaporation of a black hole. So black hole, even though for black hole formed from a pure state, but for all purposes, from local measurement, microscopic observations, for all purposes, black hole behave like some kind of thermal state. And if you approximate it using a thermal density matrix, and works extremely well. And so there was a important proposal by Page. He said that if you look at, say, Renyi entropies or entanglement entropies, so here N refers to all different Renyi entropies, and N equal to 1 should be considered as a Von-Neumann entropy. So if you look at, say, those quantum informational quantities, then say A is some subsystem, respect some subsystem, and A bar is complement. And then for pure state, they should satisfy this constraint. So the Renyi entropy for some subsystem A should be equal to its complement. And this is not satisfied by mixed states. So if you can access this kind of quantum information, and if you can access both A and A bar, and then you should be able to tell what's a pure state or what's a mixed state. So this observable also have the advantage, say, than the usual correlation functions. So if you consider some correlation functions, you may see a deviation from thermal behavior. But it's still a deviation from thermal behavior does not tell you somehow this is not the density matrix. You can still have some kind of non-thermal kind of density operator. So this criteria is very sharp using quantum information. But in general, it's very hard to compute such kind of quantum information quantities, say like Renyi entropies for general system. And there's a standard trick is instead of computing, say, such quantity directly, say you assume you have a finite dimensional Hilbert space. Yeah, and then you try to calculate the average of all pure states. Okay, and such average is much easier to calculate. And so this is the famous result from by Lupkin, Sasnoid, and also Page. Is that if you average, say, your Renyi, your entropies over all pure state, then of course unitarity is still satisfied through the average process. And then you find this very nice behavior. So dA and dA bar are the dimension of Hilbert space for A and A bar subsystems. And yeah, so this formula works for A and A bar, not their size not very close. Say one of them is much smaller than the other. When their size become comparable, then the formula is a little bit more complicated. Anyway, so you get this very simple but answer which respects unitarity. And then you just assume say a typical pure state has the same behavior, and then this can give you guidance for what, say, what is the quantum information behavior for your typical equilibrium state. And this is very powerful. For example, Page used this to derive the Page curve for black hole information, for black hole evaporation, and Hayden Praskil used it to understand how the information transfer from black hole and the radiation, etc. But you do have to assume a typicality, which is a very non-trivial.
Sorry. If your Hilbert space is d-dimensional, then this average is done by using a measure that's UD invariant.
Sorry, say it again. I didn't hear the first part of your sentence.
Suppose you were working with a d-dimensional Hilbert space.
Yeah.
You need to specify the measure with which you are doing this averaging. So you choose the unique UD invariant measure, right?
That's right. That's right. You use the standard Haar measure for the unitary matrix. Yeah.
Yeah. Another question. Let's see.
Yeah.
This is true of this result of Lubkin and Lloyd and so on. Is true for any n, for all n.
Yeah, it's actually it works for any n. So of course, when A and A bar become close, then the answer become different for different n. So so this answer applies for say for A and A bar, their size not very close. Say DA and DA bar, say they're not, one of them is much smaller than the other, and then you get this answer for all n. When DA become, say, when DA is equal to DA bar, and then, for example, then you will get independence.
I see. Thank you.
Gautam was asking, the log makes it sound like this is the entanglement entropy, not the nth Rene entropy. He was asking whether the right-hand side works only for the entanglement entropies, also for the nth Rene entropies.
Yeah, works for any Rene entropies. Including
this log term also.
Yeah, that's right. Yeah.
Okay.
Yeah, works for any Rene entropies, and its right-hand side is independent of n, and it will depend on n specific Rene entropies when DA and DA bar become close. Actually, you will see an example which I mentioned later. Yeah. Good.
Hung, can I ask a question? So,
yeah, sure.
You know, like when this two Rene entropies are equal for all n's, can we say that the state should be pure? Like, does the implication work in the reverse?
Yeah, I don't. I believe the answer is yes, but I don't. I believe the answer is yes. Yeah, but I'm not sure there's a precise proof, or there's yeah.
Okay. Mm-hmm. So is there something that can be said about, let's say, if first few Rene entropies are not equal and higher Rene entropies are equal? I mean, is there a sense in which we can say how mixed a state is by this criteria?
Oh yeah. So for example, if all the Rene entropy are the same, they're all given by this formula, and then for example, the smaller A, say if A is much smaller than A bar, and then the reduced density matrix for A would be maximally mixed. And when you deviate from this kind of, when they become dependent on n, and then it cannot be maximally mixed.
Okay.
Yeah. So this is approximation. So this is approximate formula, say, applies for one of the DAs much smaller than the other.
So did I understand that right? That you're saying basically, if I take the density matrix, reduced density matrix to be maximally entangled, then you would get this answer.
That's right. Yeah.
Okay. Thank you.
Good. So this average argument is very powerful, but you do have to assume typicality. Also, this does not immediately apply to finite temperature, or if you have an infinite dimensional Hilbert space, like a harmonic oscillator, or yeah, not to mention like field series to have infinite number of degrees of freedom. But anyway, this does give you hints how to guess, say often how to guess the answer in those more general situations. Yeah, but here I want to talk about methods which we found recently to calculate the entanglement entropies, yeah, linear entropies directly, and then you can actually get the von Neumann entropy for, by continuation, and without the leads, say for average or assumption of typicality. So here, just a couple of more remarks. Say, yeah, of course, we also, yeah, nothing comes for free. So we have to replace this kind of assumption of typicality by some other assumption when we do the approximation. And but you can decide. So hopefully the assumption we use here can in principle be systematically improved on, rather than, yeah, something like just assumption of typicality is not something you can improve on systematically. And also now you can directly apply to finite temperature, infinite dimensional Hilbert space, field series, etc. And also the answers actually can be solely, can be expressed solely in terms of properties of equilibrium density operator. Yeah, some equilibrium density operator. So they are independent of the details of initial states, but yet they're compatible with unitarity. And so somehow the result capture both, say, equilibrium nature of the state, but also the pure state nature. And then if you apply this approximation to say to gravity systems, in particular the black hole systems discussed recently last year, and that actually gives you a systematic derivation, say, of replica wormholes introduced in those papers to say for black hole to satisfy the page curve. In particular, this gives you actually a precise prescription. You don't have to do any guesswork, and also give you the mathematical origin of the replica wormholes. Also, give you some shed light on their physical nature and why they give result actually compatible with unitarity. So if I have time, I will also discuss some other issues. So before I proceed, do you have other questions? Good. Yeah, also I should mention, since this talk talks about, say, approximation method, and so necessarily the notations are a little bit heavy. So anytime if you forget about the earlier notations, etc., don't hesitate to ask. Yeah, because I have to use lots of notations. So so please make sure you ask. Okay, good. So let's just describe setup. So imagine we start with the initial state psi 0. So this can be a far from equilibrium state. And now let's imagine the system evolve according to some unitary evolution operator u, say to some time t, and then you get the state at some time t. So I will assume that this psi at time t is already equilibrated. So I call it an equilibrated pure state. And so I will not give you precise definition of what we mean by equilibrated, because that's actually a highly non-trivial definition. If you want to define rigorously mathematically, it's actually not easy. Okay, so what I will just assume that microscopically there exists some kind of density operator, some equilibrium density operator, which can describe, say, microscopic or local properties of this pure state very well. So I write this equilibrium density operator in terms of some unnormalized operator, which I call I alpha, and then the partition function for the I alpha. Okay, and so this partition function can be considered as the effective dimension, say, of your accessible Hilbert space. And so I will always take this effective dimension to be very large. Yeah, because I'm considering a many-body system. And then this alpha corresponding to, say, some equilibrium parameters to specify your equilibrium states, say, including things like temperature, chemical potential, etc. And yeah, so here are some examples. So for example, if you have a finite dimensional Hilbert space and at infinite temperature, by infinite temperature means means that your initial state is energetically enough that actually the evolution essentially has no energy constraint. Okay, when you have a finite dimensional Hilbert space, this is possible. And so conventionally we call it infinite temperature. So in this case, then the equilibrium state essentially just given by the identity matrix. Okay, so the whole, yeah, so you can approximate this pure state in equilibrium by such a maximally mixed density operator for the full system. Okay, and so they also say microcanonical ensemble in the case which you have energy conservation, or you have infinite dimensional Hilbert space, etc. And then you can consider some energy band I, and you only consider, say, states within that energy band. And then this ZE now give you the dimension of this energy band. So you can also have microcanonical ensemble. Yeah, say then I beta just exponential minus beta H, and then this is your standard thermal partition function. Yeah, so emphasize those are density operators for your full system. And those are just macroscopic description of your pure state. Okay, it's some kind, yeah, you can imagine them as some kind of coarse-grained description of your underlying pure state.
Sorry, so what was psi naught again? Psi naught was vacuum, or?
No, psi naught just some initial state, some far from initial, some far from equilibrium initial state. Yeah, okay. some general initial state.
General initial state, and
yeah.
U is just a particular unitary evolution or some random unitary, or what do you have?
U is just some particular U is just the evolution operator for some particular system, say with a fixed Hamiltonian.
Is the Hamiltonian the same as in point number 3?
The Hamiltonian don't have, that's right. The Hamiltonian would be in the point 3, the Hamiltonian would be the same as that Hamiltonian. That's right.
Thank you.
Yeah. So here we are not going to do any averages. So you always imagine there's some specific quantum system, and that a specific quantum system have some Hamiltonian, and U is the evolution operator for that Hamiltonian at some time t. So I will assume t is not too small, so that you have under the evolution you have already achieved the equilibrium at least macroscopically. Yeah.
Hong, can I ask a question? So, when you say that this state is macroscopically well described by an equilibrium density operator, you don't mean kind of local equivalence like the reduced density matrix in the state psi is the same as the reduced density matrix in state rho E for small subregions. You mean something more than that. Macroscopic, you say macroscopically described by this.
Yeah, so this is the, by macroscopically, I mean, say you can characterize this state. Yeah, at some level, I do mean what you said, but also implies, say, some other more coarse-grained quantities. Say, if you measure the total energy density and measure the temperature, or such kind of macroscopic parameters, and then you find some thermodynamic relation are satisfied. Yeah, so those things can be global quantities.
I see.
But some kind of cross-grained global quantities. Yeah.
Can I ask a question, Hong?
Yeah.
So you are saying that if you take any system of finite dimension, then asymptotically, in some sense, you will get this density matrix in point number 3. Is it obvious, or you can have systems which don't equilibrate actually?
Sorry, say it again.
See, I mean, I'm a little bit confused about what's going on. So you start with a state psi naught, you evolve it for large times to get the state psi, and that system can be approximately the averages, expectation values of operators can be evaluated using the canonical ensemble 3.
That's right.
Right. Now, it's not always guaranteed to happen that this will happen, right?
Yeah, that's a good point. So that's what I said, that actually to define, so this is related to how you define precisely or rigorously what means by normalization. And so normally we define normalization by, say, if you measure some few body operators corresponding to some local measurements, and the expectation value of those few body operators then are exactly the same as this canonic, say in the 3 case, the same as the average in this density matrix. And so here that's that's the standard, say, heuristic definition of your what we mean by normalization. Then, of course, the tricky thing here to define precisely is that what class of operators you should allow to satisfy these properties. And typically we say few body operators, and but if you have infinite dimensional Hilbert space, then there can be other tricky questions. So I'm not going to go into detail. So how we precisely define normalization, etc., is not what we want to go into here. Here, I'm just assuming, say, suppose you can define a precise notion, say, of normalization, and within that notion of normalization, and then those are the density operators you would use to approximately to describe your pure state.
Okay.
After normalization.
Thank you.
Good. So so this I alpha, this notation will be used a lot. So this is unrenormalized density operator, and I will often call it to be an effective identity because, for example, in the finite dimensional case, this is just the identity operator, and for the microcanonical ensemble, is the effective identity in your microcanonical band of states. And so I will sometimes call this I alpha to be the effective identity. Good. So now let's talk about the Renyi entropies. So here is the definition of the Renyi entropies. So we take U0, 0, then you evolve it by this evolution operator U. So you get the density operator at time t. Then you first take the trace A bar. Okay, so inside this parenthesis, then you get the reduced density operator for A, and then you take power n. Then you take trace A, and then this is defined to be exponential minus n minus 1, say the Renyi entropy. Okay, so the whole thing is like some kind of free energy. Whole thing is like some kind of partition function, and the Renyi entropy is it's more like some kind of free energy for this partition function. And so von Neumann entropy is defined by you take n go to 1 limit. Okay. I always will think about the von Neumann entropy as n goes to 1 limit. Good. So now if you think about in the path integral language, so each unitary operator, say, is represented by some path integral from time 0 to time t. Okay. And now to define this Renyi entropy, nth Renyi entropy, then you actually have 2 NUs here. So that means if you write it in terms of path integral language, there are 2n path integration contour. Okay, so here I use this figure to represent it. So the figure going upwards, so this corresponding to U, and going downwards, this is like U dagger. So you have n pairs of u and u dagger. Okay, and so if you write in path integral language, you will have 2n path integrals, and the initial state of this path integral is specified by your initial density operator rho 0, which is a pure state, and then the final condition of this path integral are specified by those partial traces. Okay, so those partial traces give you specifications for certain contractions. So that's essentially specify your final conditions for this path integral. And the integrands, I will not write this path integral carefully. And the integrand of this path integral, of course, is this familiar phase factor, goes 1 into n, phi, which going forward, which I call them, phi is the dynamic variable for the path integral go forward, and the phi prime are the dynamical variable for the path integral going backwards in time, corresponding to u dagger. And so you have this I s phi I minus s phi I prime. Okay. And again, this ZA, which is defined as an exponential of the Rayleigh entropy, will be used, this location will be used over and over. Okay. And so keep in mind this location. Good. So we have this, so we have this path integral representation for this Rayleigh entropy. And now here is an important observation, which actually was made by Zhou and Nahum in considering a related question. And there's actually a special subset of configurations within this path integral. So those are the configurations which phi I corresponding to dynamic variable going forward in time, and those dynamic variable going backwards in time, they are paired in some way. So phi IT is related to phi prime I through some of the phi I prime. Okay, so for example, you compare phi 1 with phi 2 prime or phi 1 prime with phi 2, etc. And so, so you can do, say, arbitrary permutations between the indices as far as you take phi I to be they paired through arbitrary permutations, and then this exponent is always 0. Okay, and then this phase factor in your path integral then is 0 for this special set of for this special subset of configurations. So emphasize these are not saddle point; they're just configurations. Okay, just subset of configurations. And so now you can imagine, say, if your time is actually is sufficiently long, and then the system is sufficiently chaotic. Okay, and then maybe for generic configurations phi and phi I prime, which is not paired as this, such kind of phase factor may become very large. Okay, and then the contribution from the other configurations may integrate to something very small. Okay, and then it's natural to expect such kind of configuration actually may dominate the path integral. Okay, they may dominate the path integral. And and then say if you are interested, say, in the equilibrium properties, maybe you can just focus on this subset of configurations. Okay. And in particular, when you have these configurations, when they are paired, then this phase factor becomes 0, then the whole integrand becomes 1. Essentially, you lose the time dependence. There's no longer time dependence because the time dependence in your path integral comes from integrating this non-trivial integrand. So when you consider this configuration, the contribution from such kind of configuration are independent of time. So it's natural that actually they may describe time-independent expressions. Okay, they actually describe your equilibrium properties.
I have one question actually, Hong.
Yeah.
Sorry. What is this I doing in front of the action actually? I mean, I would be more comfortable with your argument if there was no I and just like in ordinary statistical mechanics. But what is this I? That means it's
because here we are considering a Lorentzian path integral, right? Because we are doing a real-time evolution. We're doing a real-time evolution. So this is just ordinary time path in ordinary Lorentzian path integral. Yeah.
So, but so this argument still is valid.
Yeah, because if you have a very large phase, whether you have an I or large, actually, so if you have a very large phase, and then with the I, they still will integrate to 0.
I see. Okay, because it oscillates very fast. Okay, thank you.
That will oscillate very fast, but if you have many such kind of configurations, when you add them together, then they give you something typically very small.
Thank you.
Yeah.
So, I mean, usually if you have something with a phase, wouldn't we extremize this phase? I mean, like, shouldn't you consider only the phase which I said that the phase is, I mean, it's a saddle point, it extremizes the phase, like rather than setting the phase to 0?
Yeah, here it's actually more than stationary, because the here is just observation. For this here we are not doing any side point approximation, and you just say, let's imagine, here is just observation for this set of configurations, the phase is just identically 0. And then now you can ask, say, suppose there are some other side points. How does the contribution of those side points? So if you have some kind of typical side point, it's actually normally hard to define the side point in this kind of, say, many path integrals. Anyway, suppose you find some other side points, and so that side point will still depend on time. And the integration that may still lead to some answer which are, say, at large time, say, fluctuates very fast. And so there's a reason even those side point may not be important. But of course these are very heuristic arguments.
This configuration you've looked at is a saddle point because it preserves the symmetry, right?
No, this is not a saddle point. This is just subset of configurations.
But if I ask, I look at this subset and I ask, does it extremize this action? Does it or not?
It does not have to. Just say if you do the variation near this configuration, I don't think it's necessarily that the first variation will vanish.
I had thought it might, because it preserves the symmetry. Usually symmetric configurations, if you move one way or move the other.
No, if you say if I consider this configuration, say if I vary around this configuration in the full configuration space, then typical variations will not be paired, and then typically this will not vanish.
But if that's the case, why this configuration gives 0 phase, but something nearby to it gives very fast phase?
That's right.
So then I don't understand even intuitively why this should dominate.
Sorry, your voice is a little bit breaking.
I'm sorry. I'm sorry. Can you hear?
Yeah, I can hear you now. Yeah.
I'm saying that you've identified if it does not extremize, then you've identified a very special configuration. But now we have to do integral over nearby configurations.
That's right.
And it would, if it does not extremize, then the fast variation of phase in the nearby configuration should kill even this configuration, right?
So you say you're asking how would the nearby configurations contribute? Is that what you're asking?
Yeah, I'm saying that if the nearby configurations, the phase would not disappear in them, and the integrating over the phase because of nearby configurations looks like it would kill the contribution of this configuration if it does not extremize the phase.
Yeah, we are not extremizing the phase. Yeah, we are not extremizing the phase.
Yeah, but what I'm not understanding is what is the intuition to say that this configuration, and I suppose you mean this configuration and the band of configurations near to it, give you the dominant contribution.
Yeah, because if you think about the standard argument for the stationary phase, it just say somehow around some side point, your phase become slower varying than other points. So here, so this is a multiple dimensional space, and we say just within this multiple, actually for infinite dimensional systems, this is an infinite dimensional space, and for such a subset of for this subspace, the phase is just identically 0, and maybe the important contribution just in this subspace.
Yeah, sorry, but just to understand, I mean, any particular configuration, of course, gives 0 contribution, right? Because it's measure 0. You need to look at a neighborhood of a configuration. And I thought the usual argument was that in that neighborhood, you will get a vanishing contribution, a very small contribution, unless it extremizes.
No, not necessarily. Now I'm looking at the, I'm not looking at not a single point. I'm looking at the whole submanifold. I'm claiming, I'm just giving you a heuristic picture that this whole submanifold, maybe the dominant contribution comes from this submanifold. I'm not saying any point of this submanifold is important. I'm just saying you can just focus on this submanifold.
But the submanifold is some codimension submanifold, right? So it's submanifold is 0 measure on the space of all configurations.
Yeah.
So the submanifold itself gives 0 contribution. I presume you mean in configurations in the neighborhood of the submanifold.
No, the submanifold itself does not necessarily give you 0 contribution, because the they can well give you a finite contribution.
Yeah,
I'm sorry to go on, but last, and then I'll stop. Suppose I have an integral over x and y, 2 variables. You look at the submanifold x is equal to y. That gives 0 contribution. It's only in the neighborhood of that you can hope to get a non-zero contribution.
No. That's you're assuming that that's what say. No, that does not give you 0 contribution, right? It does not. It give you a contribution which is proportional to the to the volume of the submanifold, and the volume of the submanifold can also be finite.
But the volume of the submanifold is 0. It has an area, but not a volume. We can ask later.
No. It's some number, right? It's the yeah. I'm just saying you are doing some integration, and suppose you integrate.
Suppose we're doing a 2-dimensional.
No, you don't necessarily. I think you are assuming that somehow you normalize the answer by the volume of the total configuration space. That's not what we do, right? Yeah, because if most contributions, if the whole volume contribution, they all give you 0, and then only the sub-configuration will dominate, then that's fine. You're not normalizing this by the total volume of your configuration space. And your argument
Wait,
works.
You're doing
yeah?
You're doing an integral, and as for that integral, it just gives you a 0 measure contribution. I mean, suppose I was doing a dr d phi 2-dimensional integral. The integral over phi at any given r is 0 measure. In the neighborhood of some r, it's non-zero. It's something times dr. No, I'll ask you later.
No. Imagine I have an integral, say dx dy.
Yes.
So imagine I have an integral dx dy fxy.
Yes.
Okay.
Yes.
So now let's imagine fxy is proportional to delta x minus y fx. That still give you a finite answer. No, that still give you a finite answer.
Proportional to what? Is proportional, fxy is proportional to?
Yeah, just imagine fxy is proportional to delta x minus y, Dirac data function x minus y times some arbitrary function of x. So that still give you a finite.
Yes, that gives something finite because you have the delta function.
Sorry?
Because if you didn't have a delta function, if you had something smooth, then no particular manifold would give you a finite function.
No, I can approximate that delta function by any smooth function. And you can imagine that the function is just a limit of that smooth function.
But then you have to consider integration from the neighborhood of that smooth function.
Exactly.
Yeah, you will. You just suppose your nature of your integrand is somehow somehow say behaves like some kind of regulated data function, and say somehow when you take say some limit, say the number of degrees freedom going to infinity limit, somehow that integrand somehow become a data function. And then, yeah, then this is like that kind of situation.
But sorry, Hong, I'm really sorry, but it seems to me that this thing does extremize. Suppose I had two variables, x and y. And my permutation was x goes to y. Now I switch to the variables x plus y and x minus y.
Okay.
Okay. So now under this permutation, x plus y is even, x minus y is odd.
Okay.
Okay. Now, if I've got an action that is invariant under this permutations, it will have only even powers in x minus y. And therefore, the configuration x minus y equals 0 will extremize.
Okay.
I was wondering whether, anyway, I will ask you later. Please go on. I'm sorry to take up so much.
Yeah.
But I don't know whether permutation is a symmetry of this action.
It looks like a symmetry up to sign, right? Or not?
Well,
that was confusing. Yes. Thank you, Spencer. That was confusing.
Yeah. I don't think the I don't think this is extreme. Yeah, but let me think about it. Just yeah.
Thank you.
Okay. Good. So yeah, again, so this sigma, this notation.
Sorry,
sigma. Sorry.
Sorry, slightly different point. So, you know, if you in this whole manifold of configurations, if you want to look for stationary phase, then this particular manifold is submanifold does give you 0. But in the neighborhood of that, you know, usually you would expect the locus of stationary phase to be half dimensional, the Lefschetz symbol. And then this is a very small dimensional thing in the total dimensional configuration space. So in the neighborhood of that, you would also expect some sub-zero contribution configurations, right?
Right. No, I'm not going to do side point within this configuration. No, here just a heuristic, very heuristic argument to motivate what I'm going to do a little bit later. What I'm going to do a little bit later is very different from this. Yeah, this is just a purely, really just give you some very rough physical intuition. Mathematically, I'm not actually using any of this.
I see. And one more question: the boundary conditions at the top how are they compatible? How does one make them compatible with this locus? Is there no issue with that?
No, the boundary condition. No, the boundary condition. They are they of course don't satisfy. They don't have these properties. And then, so if you say impose these kind of configurations, and then you also restrict to certain configurations which will fit into that kind of boundary condition. Yeah. I think you can directly set this into the particle, still get the expression. But yeah, but anyway, this is all very heuristic. But I think this is a very good discussion. What I want to say is that if you're naively doing this in your path integral, you actually get the divergent answer. The reason is very simple. It's actually, you also integrate over all those configurations. Even this is a subset of a configuration, but even within this configuration contain all those trajectories which corresponding to you have very high energies, okay? So if you have a system with an infinite dimensional Hilbert space, and then that will just leads to divergences. Anyway, so this is just a heuristic argument to tell you somehow the permutation group should play some role here, okay? So now I'm going to develop a mathematical scheme to realize this heuristic idea, okay? To realize this heuristic idea. And so the key element is to realize that which is a trick which is often used in the condensed matter literature or quantum information literature, is that you can view the Rayleigh entropy or this partition function for the Rayleigh entropy as a transition amplitude in this 2n-dimensional Hilbert space with this unitary evolution operator. Yeah, so this is very intuitive from this particle picture. So each line, then yeah, so H is your original Hilbert space. So each line then represents the evolution in one Hilbert space. And then it's convenient to do a time reversal in this U dagger line, so that you define a H bar, which is related to the original H by some time reversal. And then you can rewrite the whole thing as just also rewrite the U dagger as U, okay, in this time reversal space. Anyway, so now you can just, and now this have a picture of a transition amplitude in this 2n-dimensional Hilbert, 2n copies of your original Hilbert space, and with this unitary evolution operator. And the rho zero provides the initial states in this 2n-dimensional Hilbert space, and those trace conditions defines the final states of your in this 2n-dimensional in these 2n copies of Hilbert space. So more explicitly, they can be written in some kind of compact notation as the following. And here, yeah, we explain what those notation means. So here you should imagine this rho zero E and this state, they all are some states defined in these 2n copies of the original Hilbert space. Okay. So so now let me try to define the dot state precisely. So here I'm just talking about the mathematical observation. So if you have any operator O, say in your original acting on your original Hilbert space, then you can actually define a set of n factorial states. So each one associated with a permutation group, element of the permutation group, as the following. So for each operator, you can define the n factorial states, which as this. So I will define these states in terms of the matrix element, say in some basis for this H and in this space. So I can choose a basis for H times H bar to the power n using this basis vector, say I1 corresponding to, say in the H1, I1 prime bar corresponding to a basis for H bar 1 and etc. Okay, so this is a base vector for this 2n copies of your Hilbert space. And then I can define this state O sigma just by the matrix element of O in the original Hilbert space. And then the sigma is defined through this permutation. Okay. So, so I let you to look at this formula a little bit, because this may not be very intuitive in the first sight.
So the claim is any operator O acting on this big space has this presentation?
No, the claim is that any O acting on the original Hilbert space, I can always construct a state in this replica space using this original matrix element.
I see. Okay.
Hong, it appears to me that this introduces some braiding in the original diagram. If you go back to the previous slide,
yeah,
then there are these vertical lines, right?
Yeah.
And if you allow these permutation groups, it appears to be like it introduces some braiding, let's say between phi1 prime and phi2,
yeah,
and etc. But in the original diagram, it seems that there is no such braiding. I mean, maybe another way of saying this is you were probably introducing some replica of diagonal matrix elements.
Yeah, they certainly included. They are included because, for example, those configurations which are certainly in the configuration of the original path integral, they are braided in the sense they are braided.
But in your trace prescription, aren't you supposed to connect phi1 with phi1 prime only, or phi2 with phi2 prime only?
Sorry, which one are you asking?
let's say, look at those diagrams. So there is a trace A bar that you have to do many times.
Yeah.
So doesn't that mean that phi1 has to be necessarily connected with phi1 prime all the time and not phi1 with phi2 prime, let's say? I'm saying that, you know.
You're talking about specific boundary conditions?
I'm saying that, okay, how is trace, this is related to the question that Abhijit was also asking. This trace A bar.
Yeah.
What does it correspond to? Does it?
Yeah, I didn't write down the explicit formula. So the trace A bar corresponding to, for example, you identify for the phi prime. So yeah, if you look at the original formula, yeah, I think, yeah, let me just go back to the original formula.
Yes.
So in the original formula, you first take the trace A bar,
right,
and then you take the power n. Okay, so the trace A bar is straightforward. You just identify, say, the configurations, say in the so the trace A bar is just the standard the trace, but the trace A then involving a matrix modification, then that will involve different copies.
I see. Yeah. Okay. Well, let's go on. Maybe I'll also think about it.
Yeah. So trace A bar, we are just identify within each, say phi1 with phi1 prime, phi2 with phi2 prime in the A bar subspace. But trace A, because you involve matrix multiplications, that will connect different copies. So this is the same as the standard this kind of multiple branch version of your standard the standard picture for the Euclidean story.
All right.
Okay, good.
Thank you.
So you can also define something similar for the identity operator. And then for the identity operator, you can define n factorial state. And then that essentially just define certain kind of contraction scheme. Okay. So the states corresponding to the identity operator just corresponding to different contraction scheme. For example, say, let's denote E to be the identity permutation, and the eta is the very specific one corresponding to this kind of cycle structure. I'm using the standard cycle structure for permutation. So this means n under the action of eta, n will go to n minus 1, n minus 1 go to n minus 2, and 2 go to 1, and 1 go to n, etc. Okay, so
I can think of this state earlier that we defined the n factorial states as first acting with O and then permuting the n strands, right?
That you can heuristic think that way, yeah, but this is just a precise, this is a precise mathematical definition. Say if you give me matrix element in the original Hilbert space, then I can construct this state using the overlap with the with this basis. So this is just a trick to obtain this kind of formulas. For example, if you take O associated with identity, so the state for O constructed for O associated with identity, and then contracted with the state from the identity operator corresponding to identity permutation, and then you just get traced to the O power n. And then if you take O associated with the identity permutation and contracted with this particular permutation associated with the identity operator, and then you get traced to the n to the power n, trace O to the power n. And then if you get other permutations, and then you will get other trace structure. Okay, so this is just like a trick to give you a different kind of trace structure.
Sorry, Hong. This eta is how should I think of eta? Is it that 1 is taken to n, 2 is taken to n minus 1, and so on?
No, it's the n. It's n taken to n minus 1. N minus 1 taken to n minus 2, and 2 to 1, and then.
This is the standard, the cycle notation. Okay.
That's right. That's
Thank you.
standard cycle. Yeah.
The long cycle.
Yeah. Yeah, so the eta inverse, maybe it's easier to think, eta inverse would be 1, 2 to the n, means 1 go to 2, 2 to 3, and n go to 1. Yeah, so eta is the opposite of that. Okay, yeah, so the whole purpose of those things is just to introduce, to find a mathematical way to represent those traces in the mathematical way. Okay, so now you can just write this thing in terms of this quantity, and the rho 0 E we have defined. So this is the states in these 2n copies of the Hilbert space associated with rho 0 and with identity permutation. And then this trace and trace A bar, then just corresponding to, you have identity in the A bar. As I mentioned, the contraction in the A bar is simple because you just directly contract, So for the A bar, you just have identity. But for the A subsystem, because you have a matrix multiplication, and then that's corresponding to this eta, okay, to this eta. And then this is essentially just a mathematical way to represent your original trace structure in terms of the states in these 2n copies of Hilbert space. Okay, so now let me just remind you, we have this equilibrium density operator to approximate this pure state. Okay, so now I'm going to introduce the set of states defined by this in these 2n copies of Hilbert space, defined by this this density operator. So so this density operator is an operator in your original Hilbert space. I can define using exactly the same procedure this set of states associated with that. Okay, and now I can actually define the subspace, the projector to the subspace spanned by those n factorial states. Okay, so this is n factorial states, and I can also define the projector into this subspace. And this subspace is actually not orthogonal to each other. Those states are not orthogonal to each other, so you actually have to define metric in this subspace, and then the G will be inverse, and then this define the projector, and Z2 would be the normalization of each of such a states. Okay. So now the important property of this I is that this describes your equilibrium density operator. By definition, the equilibrium density operator does not involve under the time evolution. Okay, so it does not involve under the U, and so that comes into the following. Then that leads to the following properties: is that if you act this evolution operator in this 2n in this replica space on this subset of states, actually leave this subspace invariant. Okay, leave this subspace invariant. Okay, so now you can consider decompose the identity of the full these 2n copies of your Hilbert space into this sub P, this projector, and this orthogonal projector. And now let's now look at this definition of the Rayleigh entropy, this Rayleigh partition function. And now you can just insert this identity operator on these two sides. Okay, two sides. And because of these equilibrium properties of this, because the U leaves the subspace invariant, and then this can be separated into two terms. One just corresponding to the contribution from the subspace P, and one contribution to this orthogonal space Q. Okay, and yeah, and also cross term vanishes because the because P and alpha they are orthogonal to each other. You can show because U leaves the P subspace invariant, and then there's no cross term. You just have P contribution and Q contribution. And now the proposal is that we just restrict to this contribution to the subspace P. Okay, and the Q is small. The assumption is that Q is small. And then you can just write the full answer by projecting to this subspace. Okay, to this subspace, and then that gives you this expression. So let me give you a heuristic argument. Why we think this Q projector should be small. Yeah, so this Q projector, the contribution for this Q projector can be considered. I have to somehow I have some bar there is very loading. Yeah. Anyway, yeah. So this Q can be written. Yeah. So this DQ contribution can be written as some kind of vector AQ, which defined by acting this Q projector on this. Yeah. Sorry, yeah. So this AQ corresponding to you act this Q projector on this initial state, and this BQ corresponding you act Q on this final state. Okay. So you have this structure, and if T is sufficiently large in the chaotic system, then you expect this should take this AQ to some kind of generic vector. So AQ is some specific vector, and then this should take you to a generic vector. And then you should not expect significant overlap with a particular vector BQ, because BQ is just some particular vector defined earlier. And say if the Hilbert space is very large. Okay, so that's the argument that DQ. Yeah, that's again it's a heuristic argument that this DQ is small. So this maybe can be considered as a different way to say the argument I was saying previously using this path integral language, is that somehow you can so this P projector can be considered as a mathematical procedure to project into the submanifold I mentioned earlier. And of course, this P projector is a particular way of representing the contribution of that submanifold. Okay, it's not the contribution from that full submanifold. It's some particular way to represent the contribution from that submanifold.
Sorry, Hong, maybe I don't understand, but I thought this P projector is essentially projecting onto a subspace which are equilibrated, right?
That's right.
Which don't evolve. And then this previous submanifold thing I thought was something else. How are these two things related? I mean, why is equilibration related to phi I equals phi I dagger sigma?
No. So yeah, so the common thing is that the in the configuration, yeah, here I'm just using algebraic language to describe this, say to define this subspace, and if you write this the contribution from this subspace, say in the path integral language, and again this corresponding to pairing different parts of this path integral in the using permutation group, using the element of the permutation group. But the difference is that actually you don't set them all to be equal, and because there are some weights that depend on, yeah, you don't naively just set them to be equal. You actually weight them using configurations depend on your energies or etc. Because this I alpha encodes those energetic informations. Yeah, so that's why I said the previous picture is just purely a heuristic picture, just to give you a feeling where does this computation group come from.
I see. Okay. I mean, I thought this would be more like saying that after a state evolves, it starts looking thermal, like a thermal state.
Yeah. So that's the basic idea of doing this projection. But now you want to ask somehow what this permutation group doing here. I just want to give you a heuristic picture that the permutation group can also be understood from that perspective. Yeah.
Thank you.
Yeah, because if you just think about I alpha, you say, why do I need to introduce this permutation? Yeah. Okay, so you can actually further simplify this expression. So if the system is large, of course, we always consider very large system and consider pure initial states. And then you can actually simplify this expression into something very simple, just corresponding to the overlap of this subset of these states defined by your equilibrium density operator, and overlap with this final condition, this final state which defines the trace structure for the Renyi entropies. Okay, and then you sum over all possible permutation group. Okay, so this can be considered as a compact final answer. And this is the one just a partition function for this I alpha.
Hong, I had a question. So how are you fixing your alphas? Is there a, maybe I just missed it?
Yeah, the alpha depends on your specific systems. So for example, you so I mentioned that if you have say infinite finite dimensional Hilbert space, if your initial state is actually highly energetic, and then you just take I alpha to be identity, and in this case there's no alpha. I just this script I just identity operator, and say if your initial state is sharply localized in some energy shell, and then you can take this say macrocanonical identity operator in that very shallow energy band, and this alpha would just correspond to the energy of that band. And then say if you approximate your state using canonical ensemble, using the expansion matrix beta H, and this alpha will be equal to beta. Yeah, so that depends on your specific system.
So let's say this canonical canonical ensemble example, this third. So why don't states with nearby alpha contribute? Why is only one alpha thing dominant? I just thought you have to do some integral over alpha also.
No, alpha is just determined by the, for example, if you look at the, so in that case, we determine the alpha as follows. You calculate the energy of your original states, say, calculate the energy of your psi 0. And then you calculate the expectation value for in this expansion minus beta H, and you fix that value of beta by equate their energy. So that you uniquely determine your beta.
Yeah, I'm just asking, just physically, like where is the physics of the thermal fluctuations, right? Where temperature itself can fluctuate. Or is it the statement that you're assuming that because the system is very large, somehow this temperature fluctuations are very small? I mean, I'm just
no. You are talking about the local temperature fluctuation, because here we are just consider. Just imagine you have a. Just imagine you have a gas in the box, in a very large box, and for the whole state, you can define some global temperature for that full state, and so this is that global temperature.
Okay.
Yeah, locally you may have some temperature fluctuations, but this is the global temperature for the whole state.
So, and I also wanted to try to understand what do you mean by the system being large? Are you taking a thermodynamic limit, or are you saying like something like a larger limit where even in a finite volume, the number of species itself is very large?
Yeah, you don't have to. You can take the thermodynamic limit. You can take the large n limit, or if you have a finite dimensional Hilbert space, you can just take the dimension of the Hilbert space to be large. You don't have to introduce those large n parameters. You don't have to take a thermodynamic limit. So thermodynamic limit is just one example of this. Yeah, by saying the system is large, I just mean that this Z1 have to be very large.
Okay, thanks.
So actually I'm not keeping track of the time. So what's your time?
You have some more time. You can take some more time. I mean, how long do you think?
Okay, thanks. Good. So now let me look at this. Now let me just make some comments on this expression, this final expression. So also sometimes I use this notation, define each term here to be just tau. first, this is now is expressed solely in terms of equilibrium density of operators and independent of initial states, as you would expect. Say even quantum informational properties somehow should be independent of the initial state. And so I will not go through the calculation here, but you can actually check. Explicitly the expression is actually satisfy unitarity constraints. Somehow this projection itself is compatible with unitarity.
Sorry, Hong, just a small question just to get myself oriented. So how is it, so if I go through, I mean, naively these arguments, then I seem to get to a result which says that Zn should be equal to trace rho to the n, where rho is a thermal density matrix or whatever the density matrix is, the equilibrium density matrices that you had. Yeah. This of course should be different from that, right? So in what aspects is it different from that?
Good. I'm going to comment on that immediately.
Thank you.
Yeah, I'm going to comment on that immediately. So so related to the question you were asking, if you just say naively say say this is given by the Rayleigh entropy of the trace of the thermal density, a reduced thermal density matrix. Of course, that expression will not satisfy the unitarity constraints. So the key thing is that you have those different permutations, and those different permutations help you to satisfy the unitarity constraint. And so they actually, among all those permutations here, there are two of them are particularly interesting. So one, just corresponding to you have identity here. Say take tau to be the identity permutation. And in this case, indeed, you just get the reduced density, you just get the Rayleigh entropy in this thermal state, in this equilibrium state, a density operator with respect to A. Okay, so this would be your naive answer. Okay, and your naive answer comes from the identity contribution in this permutation. And now there's another interesting contribution. Is that if you take this tau to be eta, remember eta is the one which gives you that particular kind of trace structure. If you take tau to be eta, and then you find that this is actually give you the Rayleigh entropies, Rayleigh partition functions for the A bar, equilibrium Rayleigh partition functions for the A bar. So that's come from the eta case. Okay, and so these two particular contributions have very simple physical interpretation, and then there are also others, and then their physical interpretation are more obscure. Okay, so they involve in more funny boundary kind of contractions. So you can show. I will not give you details here. If one of the A or A bar is much smaller than the other, and then you find that either tau equal to E or tau equal to eta dominates. And now you just find this answer, which is natural generalization, which one naturally expect from this kind of infinite hard random average for this finite dimensional Hilbert space. You find in this case, when one of A and A bar is much smaller than the other, you just get the entangled entropy, just all the Rayleigh entropies and the von Neumann entropies for A, just given by the minimum between the equilibrium entropies of A and A bar. Okay, and with all the other taus, they submitted. And of course, this answer is with respect to unitarity. Okay, and so now let me just briefly comment. So this is a situation, say when A, so this applies to all cases, finite temperature, infinite dimensional Hilbert space, quantum field series, etc. So now if you ask the situation when A and A bar is actually comparable, and then you have to do a little bit more. So when A and A bar are comparable, and now you have to look at how many traces are in this overlap, okay, for each tau. So now let me just mention a few facts. Is that number of A traces coming from this kind of overlap is given by the number of cycles of tau. Yeah, because tau is some permutation, they have some number of cycles, and I will denote it by k tau. And number of A bar traces then I related to the number of cycles of eta minus 1 tau. And then I denoted by k eta minus 1 tau. And then suppose, say each trace in A give you some kind of effective dimension for A. Say a trace in A bar give you some effective dimension for A bar. And then roughly heuristically, and then this each contribution here then have a structure like Ka to the power K, the number of cycles for the eta minus 1 tau, and for A bar, just number of cycles for tau. And if when A and A bar become comparable, then your leading contribution, then you want to maximize the sum of these two. Okay, because A and A bar become comparable, so both factors are of comparable. dA and dA bar comparable, and now you want to maximize the sum of these. But now note a simple fact is that the number of cycles associated with tau and the cycles associated with eta minus 1 tau is actually smaller than n plus 1. So this n is the number of the it's your permutation group. And the one which saturated, they are one can show that they are one-to-one correspondence with so-called long-crossing partitions. Long-crossing partitions corresponding to, say, if you have n numbers, then you can partition them in a certain way, and then different subset of the partition, they don't cross each other. Anyway, there are some ways to define them. If you are interested, I have a backup slides. You can take a look, or I can explain later. Anyway, so this is saturated when you have these permutations corresponding to long-crossing partitions. And then actually one can make this structure manifest by associate the diagrammatic structure to this kind of overlaps. Okay, and I will not explain to you where does those how to obtain those diagrams, but let me just explain to you that actually one can define those. Because those, this quantity essentially just tells you a certain kind of contraction of indices. Okay, how A and A bar, they should contract in a certain way. So you can represent those contractions in terms of diagrams. And then you have here, the only thing I emphasize in those diagrams is that you have these circle loops of the solid line, then that's corresponding to each A trace. And then you have loops of the dashed line, then that's corresponding to the loops of the A bar subspace. And then those shaded region then corresponding to the matrix element of this I alpha. Okay, you contraction this I alpha, and so you can get the, and then those non-crossing partitions which saturate this inequality, then corresponding to planar diagrams. And the planar diagram saturates this inequality. It just precisely equal to n plus 1. Okay, so that maximized number of total number of the A traces and A bar traces. You can also have non-planar diagrams, which then you have smaller number of traces, a smaller number of total traces. So in the case which you have A and A bar become comparable, then you'd have to sum over all planar diagrams, in addition to this tau equal to eta and tau equal to tau. So these are, for example, these are two examples for tau equal to eta and tau equal to tau. And for example, these are some other examples for some other taus. Okay, good. So let me also make some remarks that, so this expression, you can also express it because this just tells you how to do various contractions of the matrix elements, say of the I alpha. And so you can also represent it in terms of Euclidean path integral for I alpha. So now essentially you convert this random quantity in terms of Euclidean path integrals for I alpha. So now here I give you some examples. Say if you consider n equal to 3, and if you consider the canonical ensemble, say I alpha given by expansion minus beta h, and then for identity, for tau equal to identity, then that's corresponding to this kind of contractions. Say so this is corresponding to evolution from 0 to beta, and so for tau equal to e, for A bar, just doing the trace for each within each copy, and then for A, you connect them like this. So yeah, so this is just the standard contraction. Say, yeah, as I mentioned, for tau equal to E, you just get the standard contraction for the Rayleigh entropies of I. And for tau equal to eta, and then you get the corresponding contractions just as you are calculating the Rayleigh entropies for A bar. Okay, so you identify A, and then you can have more other tau, and then corresponding to more exotic contractions. But they all systematically specified by this permutation group. Okay, and so there's n factorial diagrams, and then you need to sum over them, and then you decide, and then for specific systems, then you decide which diagrams dominate. Okay.
Right, so the first one is the Rayleigh entropy in just the ensemble Z alpha.
That's right. Yeah. So the first one is just the Rayleigh entropy respect to A in the ensemble, and the second diagram just corresponding to the Rayleigh entropy for A bar, just for the equilibrium density operator. And then for other more general permutations, then you have more exotic diagrams.
Hong, sorry, this may be a bit vague, but conceptually I'm having problem understanding why is it that I shouldn't just look at the first figure only. What is it that? So what was missing in computing this naively? Is there a more conceptual answer to this?
Yeah. First, you said if you just naively look at that, then it's not unitarity invariant. It does not respect unitarity. And so this projection procedure give you a way. Somehow when you think of this QN replica space, all these n factorial states, they come together. They all naturally come together. And when they include all of them together, you get unitary answers. But if you only look at subset of them in some artificial way, and then of course you don't get the answer which respect unitarity. Well, of course, depend on specific systems, and then only certain sub-diagrams dominate, etc. And then that will also give you by looking at the dominant diagrams, of course, that will also give you the unitary. Yeah, the answer is respect.
So perhaps I can phrase it another way. So how is this different from computing the rho to the n using just the standard replica trick of some density matrix with the replica, n replicas connecting to each other in a standard way, which is like figure 1. So yeah, that is certainly not the question, I guess. But so what is the difference between these two questions?
Oh, yeah.
This is a very basic question, perhaps.
Yeah. Your first question, say if you just have some density matrix operator rho, you want to directly compute the Rayleigh entropy. The problem is that we don't know how to calculate that. That's a very complicated thing to calculate. We don't know how to calculate that. So here I'm giving you approximation to reduce that calculation into something we know. So essentially every term in this expression, now we know how to calculate. We can just use the equilibrium density matrix to calculate it. So your first question is the goal we want to achieve, but then you use the fact that somehow that rho is kind of special in the sense it exhibits equilibrium properties. And then I use that fact to develop approximation. And then in this approximation, now in principle, I can calculate all terms here using the standard technique now.
Okay, thank you.
Yeah.
Hong?
Yeah.
So is this a correct statement that if A was a very small part, A was much smaller than A bar,
yeah,
the first diagram will basically dominate?
That's right.
Said that. I'm just trying to confirm that I understood that right.
Yeah, that's right.
Whereas if A bar is very small, then the second diagram will dominate.
That's right.
Okay. So the point is that, if neither A and A bar are very small, then, other diagrams might also become important.
That's right. But yeah, but they become comparable, and then other diagram may become important.
So basically, I think, you know, like, so the statement is that, you know, like if A is very small, then I can approximate its density matrix by an equilibrium density matrix. But if A bar is very small, I can approximate its density matrix by an equilibrium density matrix. But if A and A bar are comparable, I cannot really do it, and I have to kind of do something more involved.
That's right. That's right.
And,
Also, this tells you that if A is very large, much greater than A bar, then the reigning entropies for A is just given by that of A bar. Yeah.
Right. And so this is a prescription which kind of, you know, like interpolates between these two limits, where A is very large and A bar is very large, in a way that, you know, that keeps the reigning entropies of A and A bar equal.
That's right. Yeah.
Okay.
Yeah. So of course, when A and A bar are much smaller than the other, this is the answer people normally guessed from just this, from the intuition obtained from the when you do hard random averages, say, of the finite dimensional Hilbert space. So this can be considered as a derivation, some kind of systematic derivation, show it actually indeed this intuition is correct, even when you do field theory. Yeah, good. So now let me just, now you can just apply this to whatever your favorite I alpha, okay, and then calculate such kind of quantities. So let me give you a very simple example. Say if you consider finite D and the infinite temperature, so in the case this just given by the identity operator, the total dimension of the Hilbert space is D. And then let's consider this regime, dA and dA bar, they're comparable, okay? And we take D to infinity, but their ratio to be finite. And in this case, you actually have to sum over all diagrams. And because this is finite dimensional Hilbert space, you get something very simple. And you get just this kind of expression. And this N, and the N come from summing over all planar diagrams, okay? Now you have to sum over all planar diagrams, not just tau equal to E and eta. And so this is given by the number of long crossing partitions, say, of an object into K groups. Anyway, so this is some kind of expression you can get. Yeah, so let me also mention by passing that this is actually the same answer as you would do the hard random average. So so this is the thing I should have mentioned earlier, but I forgot. Is that for this infinite temperature finite dimensional Hilbert space case, this approximation is actually identical to the hard random average, and so the answer is actually the same. Okay, so this just confirms that Good. So now let's consider gravity systems. So now we can try to apply such kind of prescription to the gravity systems in some equilibrated pure states. For example, to a black hole. Okay, so black hole, even if it's a pure state, microscopically looks like a thermal state. And now we can try to apply this to that. And now in this equilibrium approximation, now when you apply to gravity system, then this kind of overlap should be interpreted as amplitude in the full quantum gravity theory. Okay, so these are exact amplitude. Yeah, these are amplitude in the full quantum gravitational theory, which you should define. And say if the gravity respect the usual rules of quantum mechanics, then this prescription will lead to answers which consistent with unitarity. Okay, and but of course, if gravity does not respect the usual rules of quantum mechanics, and if you apply this to a gravity, you may not get something which is respect unitarity, and then that will show it. Good. And then, so as I emphasize, those matrix elements amplitude should be understood as amplitude in the full quantum gravitational theory. And to interpret those things in the semi-classical language, which we normally use, we don't really know how to define precise quantum gravitational path integrals or such kind of transition amplitude. And so implementation of this kind of thing at semi-classical level actually could be very tricky. But if you have holographic systems, and then you can apply this to the boundary, and in the boundary, we do know how to define those kind of overlaps exactly. And then the boundary version of the prescription then provides the boundary condition for formulating the prescription for the Bach gravity. Okay, so in that case, we can just first formulate what should be the boundary kind of contraction looks like, and then you just use the standard rule of holography to deduce the Bach interpretation. So intuitively, the couplings among different replicas could lead to the replica wormholes. Okay, so geometries connecting different replica universes. So, so now let me just use the example to show you that this is indeed the case. So now let's consider, say, a model of the black hole evaporation. And so let's, for example, consider a situation where initial state is some kind of star. And then, yeah, of course, the details of initial state is not important for us, which under time evolution collapsed to form a black hole. So this corresponding to summarization, and then subsequently emit Hawking radiation. Okay. So now let's imagine the time t we are interested in is already the black hole has formed. Okay. And so this is described by some psi states at time t, and then consists of the black hole and the emitted radiation subsystem. Oh, yeah. So for simplicity, so I will take this, the Hilbert space for the radiation to have finite dimension, just have dimension n.
A question.
Yeah.
So this black hole is in EDS or is in flat space?
Yeah, yeah. I will specify that a little bit. Here, I'm just making some general statement, and then I will specify to the example discussed by this sample group so that you compare with their answer.
Okay, thank you.
Yeah. So now let's imagine just take this HR to have finite dimension n, and then there's no energy constraint. Okay. So we also assume that once black hole have emitted Hawking radiation, then the radiation are separated from the black hole, so they're no longer intact. So in this case, we can just write this equilibrium density operator in the factorized form. So one just corresponding to your radiation, which I have taken to be finite dimension, I have low energy constraints, then I can just, then the equilibrium one I just take to be the identity in the radiation subsystem. So the trace in the radiation subsystem just give you n. And then some equilibrium density operator for the black hole subsystem. Okay. So this is, and now you can just apply the, yeah, so this beta corresponding to, say, the inverse temperature for the black hole. So now you can just, and then, yeah, then this is the partition function. Yeah, let me just also emphasize to compare with the people's discussion in the in gravity. We assume that the partition function have the following structure. There's a background density of states given by this exponential S0. Okay, and then yeah, the partition black hole partition function have this kind of structure. And now just with those inputs, you can just use the formalism. Yeah, oh, right. Yeah, now let's consider the regime that these two systems are comparable in size, okay? And then exponential S0 and n go to infinity, but their ratio is finite. In this case, then you have to sum over all planar diagrams, etc. So now you can just apply this machinery to this case. You can immediately write down the answer. So this is a somewhat complicated expression, which you don't need to really understand. Let me just emphasize that this is the Rayleigh partition function for the radiation subsystem. And so now this is completely expressed in terms of the partition function for the black hole subsystem, and all this n copy partition function. So DJB is the just IB, this effective identity to the power J, and then here too. Yeah. Anyway, just use those equilibrium partition functions of the original just I beta or its powers or its higher moments, and then you can write down the answer. Okay, this comes from by summing of all planar diagrams. So now let's compare with the gravity answer. So this is just the input. From this input, you can just get this answer. So now let's compare.
I have a question.
Okay.
Sorry. Is this really an evaporation process, or it's really equilibrium that the black hole emits and absorbs?
Yeah, this is the because this is the essentially you consider essentially you consider this black hole evaporation process as to be a very slow process, so that you can so that at every time you can consider the system in the quasi-static state. So here is a description of that quasi-static state.
Okay, thanks.
Yeah. Good. Yeah. So this is this is the same approximation made in this recent paper by the Stanford group. Pennington, Pennington, Stanford, Schenker, and Young. So there they consider some black hole in ADS2 in JD gravity, and which you have a standard Lorentzian black hole, but with the end of Ward brane, which is in the green line here. So this end of Ward brane make this into a pure state. Okay. And then there's a version for this Lorentzian black hole, which is given by the standard partition function, with standard disk, say a partition function with the with some kind of the end of Ward brane contribution. Okay. So this is not exactly a thermal density operator. Exact thermal density we just have a circle. Okay, but here there's something to the end of Ward brane. So to map to this story, you can just take this equivalent density operator in our case. So our discussion does not depend on the detail of this. Yeah, does not depend on details of this equivalent density operator. You only need to use the information of these partition functions. Okay, so to compare with their structure, you can take this for such black hole. You can just take it to be, say, expansion minus beta h, and then you have some other factor corresponding to this the end of Ward brane. Okay, and this again, the details of this function f is not important. Just this structure represent this structure. So now our prescription tells you that when you compute this n so this calculation, you have this zj to the b corresponding to, you just take j copies of this equivalent density operator and calculate its partition function. So you can just write schematic in this form. So each arrow, solid line corresponding to, you have exponential minus beta h. And then this green dot corresponding to this f factor. And then you just contract them together this way. Okay. So this is the boundary description. And now to think about what's the Bach description, you just think about what's the Bach description for this partition function of the boundary. And although we know that the answer from the standard prescription of ADS-CFT, you just fill the Bach manifold. Okay. And now this green dots then become the end of Ward brane, and then this solid line become each boundary in this replica wormhole. Okay, so essentially the calculation of this kind of partition function just tells you have to include this kind of replica wormholes in the specific way. And then, for example, this is for n equal to 3, and then you add all the planar diagrams, and then you just add this kind of their combinatoric factors are not including here. So n is the things associated with the radiation, and then the part with the black hole then can be written those factorized. Yeah, so this is corresponding to tau equal to E, tau equal to eta, and tau equal to other cycles.
Sorry, Hong, I missed what the green things are in your case.
Yeah, green things just this F.
Okay, I see.
Yeah, this F. Yeah.
But what is it for you?
Yeah, this is just some factor you use to match with the gravity picture, qualitative match with gravity picture, because in the gravity picture, you don't have exact thermal density matrix. You have the end of Ward brane. So I just include here to include the contribution of the end of Ward brane. Yeah.
I see. Thank you.
Okay, so this structure exactly reproduce. Yeah. So you can just calculate this, and then you find that the answer is exactly the same as the gravity calculation of this Stanford group. Okay. So actually, this leads to a derivation of the, say, I would say so there they essentially introduce this kind of prescription by some kind of guesswork. Okay, but here you don't have to do any guesswork. You just apply this machinery and then just sum over all this. So physically, and also there they have speculated whether somehow when you include this kind of some kind of wormholes, a replica wormhole, does that correspond to doing some kind of random averages? But here, actually, physically, we see here, including replica wormholes, does not correspond to random averages. They actually arise in systems with fixed Hamiltonian. It just comes from some kind of specific approximation. Okay. Also, this eliminates somewhat complicated, say, in this gravity calculation, there's some kind of complicated planar diagram you want to sum over, etc. And so here we understand that the underlying mathematical structure, behind those planar diagrams, they're just long crossing permutations. Okay, and you can actually calculate those numbers exactly. Those coefficients exactly using non-crossing permutations. Yeah, just all those combinatoric factors are just from non-crossing permutations. And also in more general cases, so even though in these cases people can just based on some guesswork because we understand the JT gravity very well, etc. But now this actually provides a precise prescription. So when and how you should introduce replica wormholes. Say, for example, in higher dimensional case, when the story is more tricky, and then maybe your gravity intuition is not as good as JT gravity, and then now this procedure then can provide a precise prescription for you. So you can also consider this kind of situation considered by other people, which corresponding to an internal black hole coupled to a bath. And here I will not go into details. I'm just saying, again, if you apply exactly the same procedure, then you find that the answer is given by the black hole, the minimum between the black hole contribution and then the bath equivalent Renyi entropies. And again, the saturation comes from the replica wormhole, the similar kind of replica wormhole. So you can also consider, for example, here in this situation, only say, unless you are very close to the transition between the two, and then only two of them will contribute. Only two diagrams will contribute. So one is tau equal to E, and one is tau equal to eta, and tau equal to eta give you the replica wormholes. Which discussed in this Ayamari et al.'s paper. Okay, you can also consider some other situations. For example, you can consider a big black hole in ADS formed from collapse. And then say you can consider big black hole in ADS come from in the radial solution. And then again, just by this kind of, again, you can apply this kind of diagrams, contractions to the boundary theory. And then that gives you a prescription how you should construct the Bach partition functions for those Renyi, for each Renyi partition functions. What would be how you should say identify different parts of the boundary. Okay, and again, this corresponding to the standard one for the Renyi of A and A bar, and then the other taus corresponding to more exotic kind of identification would corresponding to more exotic manifold in the Bach. Okay, so I think I finished this discussion. I have some quick discussions, but now I see it's pretty late. So
perhaps I could say that perhaps we could let people go, whoever wants to say behind, and we could continue.
Yeah.
Okay. So before that, let's thank Hong, everyone.
Yeah, actually, I only have a couple of minutes. Very quickly, let me just say say a few things. Just very quickly say a few things. So the dynamic assumption which we have made here is that this unitary evolution operator can take you from a say general far from equilibrium state to an equilibrium state, and that we can ignore this contribution from this Q. From this Q project, the orthogonal projected to this subspace. And again, this should be considered as a dynamical properties of U. Okay. So one could speculate that somehow maybe this can be guaranteed by having U from a chaotic system. But you may want to ask, say, what aspect of the chaotic system actually can be responsible for those features, okay? So what are the dynamical physics behind it? So a hint on this kind of question can be get from the following observation which we made earlier in the earlier paper with Shreya. So you can actually show that the equilibrium behavior of the Rayleigh entropies can be actually considered as a special case, say, of a general dynamical properties of operator growth. Yeah, because of the Rayleigh, because of the density operator, just a special operator which is normalized, positive, definite, etc. But you can also look at generic evolution of an operator. Yeah, evolution of a generic operator. And there we conjecture that there's something called the random void distribution for general chaotic systems. And then this equilibrium behavior for the Rayleigh entropies, which I described, that may be considered as a special case of the general behavior of the operator growth for a chaotic system. And yeah, so perhaps this can provide some dynamical insights into those questions. Also, you may ask, when does this approximation break down? So first, say we expect this equilibrium approximation to apply to time not very short. But also should not be too long time, because as you wait for a very long time, then the fluctuations around the equilibrium can become significant. And so for such kind of time scale, then somehow yeah, some other contribution should be included. Yeah. So also there's a funny here in our discussion that the fact that you have multiple copies, that you include all these different permutations, play a very important role in the maintaining unitarity. So now you may consider, let's consider, apply to a single copy. Let's just imagine you consider correlation functions of a single operator. Okay, yeah, just the expectation value of some operator. And then if you apply this procedure, you can still apply this procedure. And then you just find that this is always given by the thermal density expectation value, no matter the nature of O. So this is a little bit funny, even though we do expect this answer to be true for O to be given by some few body operators. But when O become very large, say if you O involve more than half of the system, certainly we don't expect this to be true. So yeah, but somehow this approximation must break down somewhere when you don't have multiple copies. Yeah, because somehow there's no other permutation to save you. When you calculate the Rayleigh entropies, etc., somehow the other permutations saves you. Yeah, one can consider another situation, which is a factorized situation, which is a trivial case. Let's just consider you have trace U and trace U dagger, and then you take m's power. Okay, so this is unfactorized, trace for each U. And now you can just apply the same approximation. I should use the approximate sign here. If you just apply the same approximation to this quantity, because again, it's involving 2n copies of U, and then you find that this just involving the trace in the full replica space. Okay, so this trace hat corresponding to the trace in the full replica space. And then this evolution operator. Again, then you can separate into ZP plus ZQ project to this subspace. But now we don't expect this approximation is good. Because certainly this ZP does not give you a factorized expression. And also here, there's a simple reason that somehow you don't expect this approximation to work well. It's because here, rather than a transition amplitude, as we mentioned earlier, for the Rayleigh entropy, which you have a specific initial vector, then transition to a specific final vector. So here you actually have a trace over all space. Okay, so each transition element can be small, but when you trace over all space, yeah, when you calculate DQ, when you trace over all this replica space, this is a huge space. And so you have sum of many, many terms, even though each term may be small, and we sum of all of them still can give you order 1 contribution. So, so in this case, we don't expect, certainly, expect this to be suppressed. Okay.
Sorry,
yeah.
One question. In the second point here on the slide, I guess, so if you were to compute this answer for higher Rayleigh entropies, and then take n equals 1 limit, is it the same as doing this thing?
Yeah, that's a very good question. Yeah, so if you do, this is actually a very good question, which I didn't mention earlier. So if you do, so for the Rayleigh entropy, if you take n equal to 1, then that's just corresponding to normalization of the of your original density operator. So that statement, in a sense, does not have any dynamical information. You just corresponding to, you have to respect normalization. So we impose that condition as an input. You just say this approximation at least should respect that normalization condition for rho. Yeah, that's it. Yeah, I'm done. Yeah.
Well, thank you very much, Hong. Let's thank Hong for a wonderful talk. Questions?
Hong.
Yeah.
I want to better understand the motivation for introducing the sum over permutations.
Yeah.
So let me ask the. If you go back to one of the early slides in your talk, maybe the first or second slide, with the evolution operators going from bottom to top.
Yeah. Second. So let me try to go to the earlier one. Okay. Somehow that's not. Okay. So which slide?
You mean the first diagram? Yes, that one.
Yeah, this one. Okay.
Yeah, exactly. Okay.
Yeah.
Now, this diagram would apply for any initial density matrix. You choose your density matrix to be psi naught, but we could apply it to anything.
Yeah.
Now, in particular, suppose I chose to apply it to density matrix what do you call it? Rho alpha.
Okay.
Then we should not. Then we should just get standard answer. We should not have the thing with the sum over permutations.
Yeah.
Right, because
so
in rho alpha.
So
why is it that we have to ignore the sum over permutations there, but we have to keep it for the pure state?
Yeah, so this is related to the somehow first just say mathematically summing over the permutation is it's a natural thing to do. Say when you consider this kind of replica space. Because once you write in terms of this language, if you want to say project into this equilibrium thing, and then there's no reason why you should include one state or not the other state. They're all somehow on the mathematically they are on equal footing. So physically, somehow the physically, somehow what this replica does for you is that, yeah, let me just give you the equation, one equation. Yeah. I think this is the equation. Yeah, say if you take rho 0 to be some other density matrix, okay? So if you take this rho 0 to be just some density matrix, not a pure state.
Yes.
Just some general density operator. And then you find actually, and then this does not actually, then you actually, the information of the original rho 0 will be kept. And so you will not be able to reduce to this simple expression, which become independent of your initial state. Somehow this only happens when you somehow consider pure initial state.
No, but you could take thermophile double state.
Yeah, you can take thermophile double state, but then
you would get the standard prescription.
No, just your original thermophile double state is in the pure state in already double system, right? So now you do look at the 4 copies of original system.
No, I mean A and A bar. Let's say take A and A bar to be the same systems, and in that you consider the thermophile double state, and then you run this prescription. And would you then find the answer to be just the standard density, the standard trace prescription?
No, that depends on how you involve your. No, that depends on how you involve your thermal density, thermophile double, right? So if you just evolve your thermophile double using both copies together, then the same thing. Then it's no difference from any the system I'm considering here. And but if you, there are just some pure states, some. Thermophile double state, just a very special initial state, which is not the equivalent state.
Sorry, Hong, but just going back. Suppose I started with rho naught to be my Z alpha, rho alpha.
Yeah.
Then I thought that this projector without the sum over permutations would give you the exact answer, would give you the correct answer. Because
sorry, say it again.
And then suppose I start with my rho naught instead of psi naught to be rho alpha.
Yeah.
Now if I project without doing the sum over permutations, rho alpha goes back to rho alpha. So it just gives you the right answer.
That's right.
So then if you do the projector with the sum over permutations, it seems to be adding more, irrespective of how you approximate that sum over permutations. It seems to be giving you something new. They're taking you away from the right answer.
Sorry, say it again. I didn't hear the last part of your sentence. So if you start with that, if you start with the, let me just go here. So if you start with the, so if you start with the initial state, just given by the I alpha.
Yeah. So suppose we start with the initial state I alpha and then we apply your approximations. I want to know, do you get the right answer or do you get something extra?
So if you start with I alpha, and then this U will just leave this state invariant. Okay, this U will just leave this state invariant. And and then when you insert, so this I alpha here, then when you insert this P alpha here, we'll give you some contributions. And so that should give you, we have not checked this explicitly. This is a very good point. I believe that the other contribution should cancel. Then you should get the right answer.
Okay.
Yeah, but this is a very good question.
It would be great.
Yeah, this is a very good question. We should check it.
Hong, can I ask a question?
Yeah,
so so you have shown that the long time value of the various Renyi entropies is given by the sum over permutations and sometimes dominated by the first term. Okay, so can I say something about the reduced density matrix itself from these results?
Yeah. So in the case which, in the case when it's dominated by the first term, say by the tau equal to say identity permutation, and then the reduced density matrix then become identical to the reduced density matrix of your thermal of your equilibrium density operator.
Indeed, but if not, then it would differ somewhat.
That's right.
And do they have any kind of characterization from the kind of results that you have?
Yeah, it's hard to say. So for example, say if A is larger than half of the system, say if A is larger than A bar, and then you will find that all the Renyi entropy of A is given by that of the A bar. Okay, but all the Renyi entropies of A are given by those of A bar. So certainly in that case, the density operator for A is rather complicated. But using this thing which Shreya, which we did earlier regarding this so-called void formation, we can actually say something regarding the regarding that density operator, but not very precisely. The thing is that you can separate for anything. Say suppose A is much greater than A bar, and you want to look at the density operator for A. Right. And then you can write the density operator for A separate into the identity part and the non-identity part, which is traceless. And then what you can argue is that this non-identity part then should satisfy certain properties. And so that it can actually reproduce exactly the answer for the Renyi entropies of A bar. So there are some constraints one can say about the behavior of that kind of nature. Yeah.
I see. Thank you.
One question. I have a question. Sorry, it's late, but there's something bothering me. Hong, can you just please go back to the slide which you showed when Shiraz was asking you some questions?
Okay. You mean the path integral?
Yes.
Okay.
Yeah. So if you see this, there's a replica introduced over here. This trace A bar U rho naught U dagger to the power n, right? And lots of copies of this. It's a product. So if you represent each one of them in terms of a path integral, then interchanging the full path integrals would be a symmetry. So in particular, phi1, phi1 prime and phi2, phi2 prime, if you interchange both of them, I have a symmetry. But if you tell me that phi1 prime actually can be replaced by phi2 prime, then somehow in some hidden way you are introducing an interaction between these replicas. In some that's my question.
Yeah, I'm not sure I fully understand your question. I would say so. In this path integral, you integrate over all configurations, then weighted by some phases. And within those configurations, they are all kind of subspaces, which phi1, just phi I, and the phi j prime may have some kind of correlation.
But didn't you start with small n independent path integrals just factorized?
Yeah, but the whole path integral is, the key thing is here, you do have the initial condition and the final condition. And so that's what I mentioned earlier, I mentioned in the last slides. If you consider pure factorized trace U and trace U dagger excited, just take n power of them, then you don't expect this approximation to be valid, because because that expression then reduced to the trace over full replica space. And then all kind of contribution can, it's no longer a single vector transition to another single vector. So here it's very important, somehow it's a single vector transition to another single vector.
Okay, thanks.
Can I ask you a question? I should.
Yeah.
So, I mean, this is, I think, kind of probably related to what Shiraz and Spenta were also asking. So, like if I make this model where I start with this path integral that you're showing in the slide that is being in the screen, and I add a disorder, some kind of a braiding disorder where, there are, the disorder operators which kind of flip the copies. Okay. Mm-hmm. So I kind of introduce some random gates, in the path integral, which kind of flip the gates. And if I do that path integral, okay, it seems to me that, the kind of thing that you're getting would be coming from that. So this is kind of, you start with the, fixed Hamiltonian and you're writing this replica path integral, but but you're also doing some disorder kind of averaging in the replica space. So why am I not allowed to have this interpretation?
Right. Yeah. I don't think that's what's happening because because we are not introducing anything here. You see, when you write the answer in this form, so that's the part of the power of this algebraic language. When you write the answer in this form, and then you can just insert a complete set of states in the replica space, say around the U. And so what we are looking at, we just restrict it to a subset of states. Then of course, this complete set of states are fully equivalent to the original path integral. And by restricting to a subset of states, effectively, you are somehow restrict to some kind of sub-contribution of those path integrals. Even the direct translation of those projections to the path integrals is not easy to do. So you're not actually introducing any disorder average. You're just restricting to a subset of intermediate contributions.
Yeah. The question is whether what you're calling a subset, the configurations is it roughly seems to me that those configurations were actually not present. So it's not quite a subset.
No, they are, because you can insert a complete set of states here, right? When you compute this transition amplitude, you just insert a complete set of states here. You insert a complete set of states, and now we just restrict to a subspace of those states. So by definition, they're part of your original theory.
Only the factorized states propagate, right, in this path integral. If I cut the path integral, if I introduce a complete set, can't I just introduce a complete set with only factorized states and get this path integral?
No, I think this tells you that actually depend on how you write down your basis. Of course, you can always choose a factorized basis for your path integral. You can insert, say, a factorized basis here. Say each state of that basis have a factorized structure. That's certainly fine. I'm just choosing a different basis. I'm not doing anything additional.
Okay. Okay, just one another question, which is kind of unrelated. So this is regarding this statement that you made that, that you're getting these wormholes and with a fixed Hamiltonian. This is about the gravity discussion at the end. So Douglas Stanford, while he was giving his, talk in the strings last week, one of the things, at least I understood, is that you can indeed interpret this Renyi entropy or the entanglement entropy computations as, coming from a unitary system, but it becomes more difficult once you start thinking about correlation functions. So I was wondering whether you guys have thought about correlation functions and whether, you think the correlation functions in this kind of what you call as an equilibrium approximation will also be consistent with some kind of unitarity, constraints.
Yeah, so correlation functions, it's harder to formulate the unitarity constraints. So that's the nice thing about those Renyi entropies is that there's a very simple criterion for formulating unitarity constraints. For correlation functions, I can derive some behavior. I don't know whether that behavior is compatible with unitarity or not. I can get some behavior which is different from thermal behavior. But that doesn't tell me whether this is still from some other mixed states or from a pure state. So I think somehow for correlation functions, checking unitarity certainly is much more difficult. But you can,
sorry, I guess this
also ask just whether this approximation captures, say, behavior of certain correlation functions. I think this likely to capture behaviors of OTOC kind of correlation functions, which again require introducing multiple copies. And but would be the boring part, because this would be the contribution which already the OTOC become time independent. So not would be, say, the initial, say, exponential part, etc. So for OTOC, this would just capture the boring part of the correlation function. But I think that part might be fine. But yeah, as I mentioned at the end, if you consider, say, a single operator, yeah, by single operator, I just mean, yeah, you can, yeah, that doesn't have to be a single operator. Yeah, let me just, in my last slides, I mentioned this situation. Let me just go to the last slide. I mentioned the situation that if you only have a single copy, we don't quite understand what's going on. So of course, this O can be a product of operators, say, at different spatial points. Here, the key is the time dependence, okay? Here is time dependence. So here it's more like if you have time ordered operators, TOC, then you will only have a single copies of U and U diagram. But for OTOC, then you will have multiple copies. So for OTOC, I can imagine somehow this approximation works better. Yeah, so for single copy, I don't quite understand. Yeah, we don't quite understand what's the story here.
Sorry, Hong, one question.
Yeah.
Towards the end, you had a remark saying that one doesn't quite require this average interpretation if one wants to have a dual
Right.
of a gravity.
Right.
So this was, so there was some discussion at Strings also about this. So I think, I mean, the argument that Douglas gave seemed pretty, straightforward one, where he considered Z beta squared, let's say, of some conformal field theory. And then there should be configurations also, which would interpolate between the two circles, which seems to suggest that, that there some averaging must happen in the dual theory. So how should I understand that in this light?
Yeah, so I think here you can just explicitly see that the same kind of configuration, yeah, at least for those very explicit models, for example, the models of the Stanford group, you just can derive those answers without using any average. And they just come from doing this approximation. And so that just tells you the average really does not play a role. So now there are more tricky questions, say for this kind of situation. So if you want to calculate trace U dac to the power n, now ZQ become comparable with ZP, but there could be still a situation that even though ZQ is comparable with ZP, but the ZQ can be very rapidly fluctuating. So say with time. So if you're only interested in the average behavior, then you can do some average, and then the ZQ will drop out. And then now in that case, then you may need to do some average, and in order to extract some kind of behavior, then you have to do average. But you don't have to, yeah, but in the situation for the Rayleigh entropy, the point to emphasize is just ZQ should be small, and then yeah, just no average is needed.
Any more questions? If not, let's thank Hong for a wonderful talk.
Oh, thanks a lot for the so many great questions. Yeah, it's yeah.